you all set back there? It's a it's a special pleasure for me to introduce the next. It's a special pleasure for me to introduce the next speaker, Dr. Carol Mysels, co-organizer of this symposium. And Carol, I think this is correct. You won the Kendall Award in 1964, and that makes you the most ancient award winner here on the program today. Back in 1964, your title was Soap Films and Some Problems in Surface and Colloid Chemistry. And today it is Designing to See the Unseen or to Measure the Unmeasured. Carol Mysels.
Thank you, Tom. I probably should explain the title a little bit. To confuse the adversary, I should have perhaps added Unscrewing the Unscrutable. But I didn't. But I think that research should not be judged only by the size of grants and by the size of laboratories and the size of international cooperation and so on, but also by the fun and the pleasure that it gives the investigator. I think that at least many of us scientists are extremely fortunate to be able to make a living by doing what we like. And that has certainly been my case. And the thing that I have enjoyed mostly is designing, because I'm not so good with my hands, and I'm just a mediocre glass blowing or solderer. So all I could do is to design the apparatuses. I couldn't generally make it. That's a very good of glassmakers and electronics. And maybe I should add that experimental research, I think, is trying to see what hasn't been seen before, or trying to measure what hasn't been measured before. And then comes the theoretical part, which permits us to understand what it is that we have seen, what it is we have measured, or maybe what we should be looking for. But I think that I enjoyed mostly the trying to see and to measure the things that haven't been done before. If I can try now, that system there is unbelievable. I don't see it can possibly work. But I will try. Yes, okay. That is an apparatus from my Harvard days, graduate student. I was measuring the pH, kinetics of pH of a solution at 0 degrees. And that is a homemade glass electrode. In those days, you couldn't get an electrode that would function at the low temperatures. And there are other things here. And all of that was mounted on a board, wooden board, and then put in a jumbo door. And it fitted very nicely, and it worked very well. Except that it was surrounded by ice. Then after, sometimes the ice melted, and then the wood swelled. And that was the end of the jumbo door. And that was a catastrophe, not only in terms of the experiment, but in those days, graduate students had to pay for not only their tuition and their chemical, but also their breakage. That was the problem. So now if we go a little bit further, that is an apparatus for determining the mobility of micelles. The problem with studying micellar solutions is that micelles and monomers are in equilibrium, and if you look for what the surfactant is doing, you get an average of the two, which generally is heavily weighted for the monomers. It's hard to know what the micelles do. And Horst Heuer had the idea of taking a dye, which is very insoluble in water, but is soluble in the micelles, and then studying its movement, following its action. And that way you get to know what the micelle itself is doing without any corrections. So that is simply a tube in which the solution of the surfactant with the dye, and that's why it's red, is put. And here is some more surfactant, and then a salt bridge to some electrodes on both sides. And after you allow the thing to come to equilibrium and pass, open the stopcocks, open this stopcock and this stopcock, the micelles move, and it then moves the die, and because of the phenomena that were discussed this morning, you get quite a, you can displace quite a lot of it. And there is very little mixing because the thing is horizontal. Whereas all previous electroporation apparatus depended on density differences, this one has no density difference between the tracer solution and the on-tracer solution, so it had to be designed in this particular shape. And here are some results obtained by Stichter on the mobility of micelles as a function of concentration here, and extrapolated to 0 micellar concentration. And from that was able to calculate zeta potentials and charges and so on. This is a conductivity set of a perhaps unusual form. It has a donut to which are connected the electrodes. So the electrodes measure the resistance of the liquid in that donut. But it also has a mixing compartment which is connected to the middle part of the donut, looking from the point of view of the electrodes, which permits mixing so that the solution flows out of this compartment into the donut, divides, and then comes back into the main compartment and then is sucked down. And in this way, the cell constant, that means the geometry of the system, as far as electric current is concerned, is absolutely constant because it is the donut and independent of what's in the bottom. On the other hand, the hydraulic analytical volume is either the solution here, and that can be varied completely without changing the cell constant. As a result, you can do a titration which changes the volume here, but doesn't change the cell constant, and directly get its conductivity. That is actually commercially available through Beckman instruments. I hope I made myself clear on that. The trick is that the electric current shown by the red arrows stays in the donut and has no tendency to go out through the hydrodynamic exits because they are both at exactly the same potential since they are located in the mid-plane between the electrons. On the other hand, water can circulate, shown in blue, can come in here and circulate and come out here. So you can get very good mixing, changing volumes, but not cell constant. And that way, I would say that makes conductivity measurements either 10 times more precise or 10 times easier, depending on what you choose. And for example, here is a family of data obtained by for mixture of sodium decyl and odecyl sulfate, which could be, because there were so many and so they were so good, could be interpreted in terms not only of the CMC of the mixed system, which varies, of course, from the dodecyl to the decyl, from the dodecyl here to the decyl here, but also the composition of micelles that are in equilibrium with the CMC, as shown here. And that is something that I don't think has been well done since. Here is a very simple classical apparatus for measuring dialysis. You have a sausage casing which is held by those rings on two Teflon plugs, and the solution to be measured is shown in red here, let's say, and the solution from which into which dialysis occurs is shown here. Now the problem is to obtain continuous measurement, continuous information as to what happened during that dialysis. And for this purpose, there are two electrodes, which you see here on N, to measure the conductivity of the solution on this branch. And to make sure that has the proper composition, the system is rocked, as shown on these arrows. And here is a Teflon valve, so that the liquid can only flow in this direction, and not in the reverse direction. So as it shakes, the flow occurs, and you get a very well mixed solution. There are also air bubbles that help the mixing, and a continuous picture of what happened during dialysis. Now, that was sort of interesting because there is much talk that the activity of the solution doesn't change above the CMC, that the concentration of monomers is constant at the CMC, even though you go to higher concentration. And as a zeros approximation, that is fine. But as a first approximation, it no longer is. And here are the results that Abu Hamdiya obtained. That is the rate of dialysis, which, of course, below the CMC is quite a normal quantity. Then comes the CMC, it drops, but it does not drop to zero, but continues at a finite value, which means that the concentration of monomers, because only monomers can get through the dialysis tubing, that was shown again with by means of those insoluble dyes in the micelles, which do not cross the membrane. And the result shows that the CMC is not just a wall against which activity hits, but is soft, and activity and concentrations continue to increase above. So I was able sometimes to give a lecture whose title you can see, based on those kinds of designs. Now, so you can only turn down the light a little bit. Must be there. Well, if it's too much trouble, forget it. That is there you have brilliant colors, I can assure you, of a soft film, which are the interference colors due to the reflection of light from the two sides of the soap film, the back and the front. And such films do come to an equilibrium, at which point you can still measure their optical properties and their thickness interferometrically. And the problem was what determines that. And obviously, it was shown that it must be an equilibrium between van der Waals forces and double layer repulsions, and at low, and also the force of gravity, which always pulls the liquid out through the bottom. And, oh, thank you. The colors are brilliant. Well, so that could be a tool for measuring these forces. The problem is, how do you compress such a film to measure what is the electric force that tends to repel it to something? And the answer is that you can have a film supported by a porous medium. And now when you increase the air pressure here, of course it exerts pressure on the two sides of the film, and the liquid in between can escape into the porous medium. But the air itself cannot escape, because if the pores are fine enough, the capillary forces produce menisca who retain the air and prevent it from entering or escaping through the porous medium. So you have mechanical compression of the film, and you can measure its thickness during that time. Well, here was the instrument itself. Here is the film. It is enclosed in a ring of porcelain, porous porcelain, which has a bubble point, that is the pressure at which air displaces water of the order of 6 atmospheres, so that is plenty for our purposes. And on the other side of this ring is an open space, which then leads to the outside of this capillary. And the whole thing is enclosed in a box in which the air pressure can be increased by pumping air through here. At the bottom is a window which permits measurement of the thickness of the film. Dr. Malcolm Jones, who made those measurements, got here, for example, a pressure of 10 to the 6 dynes per centimeter. Now, for those who haven't been thinking in those units, 10 to the 6 is 45 psi for the engineers, or 1 atmosphere for the non-engineers. So the film is compressed to the pressure of roughly 1 atmosphere, and its thickness has decreased from about 300 angstrom to about 120 angstroms. That is by more than 50%. Now, the slope of this line is the kappa calculated for the solution. So there is the first direct experimental measurement of kappa and of double layer repulsion, a very simple apparatus. If you want points that fit the lines better, here is one, but it only goes to about 200, to about 1/5 of an atmosphere. Now, the other interesting application of soap film is to see what happens when they burst. And for that purpose, a simple device, which here is the film, is protected by a bottle which is square for optical purposes. A spark breaks the film, sets up a train of electric events which flash a sub-microsecond flash, which permits you to take the picture by means of a semi-transparent mirror, which directs the light to the film and then back to the camera. And here is a time delay which permits you to take pictures at different time intervals. Could I, again, put the lights down? Okay, now here is such a picture taken about 250 microseconds after the spark. And the film here is, on the outside, is quite undisturbed. The black part is a hole which propagates at the rate of about 100 miles an hour. And in between is a thickening of the film, which we call the aureole, and which has never been seen before. And what happens is that here you have the hole, and you have the undisturbed film, which is a certain surface tension and a certain thickness. And in between you have that gradual thickening, which we call the aureole, which is due to the acceleration by gradients of surface tension, giving gradients in thickness, and the shrinkage of area. And one of the interesting things is that there is a shock wave ahead of that, where the higher velocities have copped up, higher thicknesses have higher velocity than the lower thicknesses, and the result you get a shock wave. Well, to make that more scientific, oops. To measure the velocities better, we use a laser two-hole method, in which a laser beam is split into two parts, directed at the film, and the reflection goes through a camera to two photomultipliers. When the spark occurs, the film is broken and recedes here, and as it recedes, the various parts pass in front of those two beams, and by recording them and measuring that interval, you can decide what is the speed at which they move. Here is a record of it. See, here is the undisturbed film, and then as it thickens, the interference produces a decrease of intensity, then an increase, and another increase, and so over here the film breaks and comes to zero. At the second hole, the same phenomena, but at a later time. And by measuring the distance between this point, for example, and this point, we know how fast the hole moves, how fast the shock wave moves at the aureole, and if you're measuring here, we can tell how fast the hole and how fast each of those thicknesses by comparing, for example, this point to this point, and so on. The result from that is that you can obtain the compression of the surface, and separate experiments show that the molecules don't have time to escape from the surface in that time. And as a result, you get the force area curve in the whole region between about 40 angstrom, which is the normal saturated sulfide solution, and about 25 where the molecules are tightly packed. And rather interesting that the curve turns over, which means that the electric repulsion, which is visible here, continues to be overwhelming, but increasing attractive forces occur that brings the molecules closer together. So how much time do we have? This is a classical, no, let's forget it and finish. Kiss. Keep it short.
You ending right there?
But yeah, I do have better stuff.